Continuing on from our previous video, we are identifying maxima and minima on our functions within a given interval. And we've done a few examples using calculation methods. Let's take a look at graphical methods now. So in our graphical example here, we are asked to consider the graph of y equals f of x as shown below. For each of the following intervals, determine the location of all turning points over the interval and determine the absolute max and minimum values of f of x over the interval if they exist. The first interval we are asked to look at for a is negative infinity to infinity. And that means that we are looking at the entire length of our function. And so we are going to be finding the global max and the global min in this case. So let's rewrite our question down here. We'll rewrite our interval negative infinity to infinity. So, and once again, notice it's not inclusive. We can't actually reach infinity, so it's an open interval. What is the absolute maximum value of this function? Well, we see that it's an even function, and so it's going to its end behavior is going to be the same, and so it's never gonna turn and go back up. So whatever maximum value I see here is going to be the maximum value for this entire function. And if I take a look, my maximum value is going to be here at y equals 4. So let's write that out. Absolute maximum is, so what's our y value or our f of x? It's 4. And that happens at x equals -5. And our absolute minimum, there is none. There's no end to this function. It just extends down to negative infinity, which is not really a number. It doesn't really have a meaning. So we just say there's none. And let's just label our curve here f of x. All right, question B. We are looking at the interval of inclusive brackets -5 to 3. So let's re-sketch on our graph here. Where our interval is going to be, and it's going to be from -5 to 3. And let's just visually take a look. What is the highest point on this curve? So generally we want to identify, local max and mins, and also our endpoints, which in this case our endpoints are actually a local max, local maximas. And what's our highest point? Well, our absolute highest point is here. So once again, it's going to be 4 at x equals -5. So our absolute max within this interval is 4 at x equals -5. And our absolute min, I can see the lowest point is going to be here at 0, 0. So absolute minimum is 0 at x equals 0. All right, question C. And I'll just erase my marks here so we can start fresh. We're looking at the interval inclusive 0 to 5. So we're going to be looking from 0 to 5. Let's look for any turning points inside that interval, and I have a minimum value here, which is also at an endpoint. I have a local maximum right here, and then my endpoint here. All right, what is the highest point on my curve here? Well, it's going to be my local maximum here, and that's going to be at 1. So for my interval 0 to 5, my maximum is 1 at x equals 3. And my minimum is going to be not this value, but as we go, it extends further below the x-axis. So my minimum value is going to be -2 at x equals 5. And finally, question D. We are looking at the interval of -3 to 1, non-inclusive. It's an open interval. So -3 is right around here. And 1 is going to be here. Our local minimum is going to be here. And what about the maximum? Well, like normally I would want to evaluate my endpoints, but there's a problem. Let's take a look. -3 and 1. This is an open interval. So it doesn't actually reach -3 and 1, so I cannot evaluate the endpoints. So instead, I just focus on the minimum, which I saw occurred right here at 0, 0. So our minimum is 0 at x equals 0, and our maximum does not exist. So no maximum for this question. So that's a little bit easier than our previous examples. I didn't have to actually calculate the derivative or anything. I could just look at the graph, look at the curve, and visually identify the features that I was looking for. Don't forget though, make sure you're considering turning points and endpoints. So what was the purpose of all this? So we just did a number of examples in the last couple videos learning about how to identify maximum and minimum points, or extrema. And the reason is that we want to be able to answer optimization problems. So what is going on with an optimization problem? What are we talking about? Let's find out. Guidelines for optimization. First of all, basically optimization, the idea is that we want to find some maximum or minimum value. We're going to have some situation where I want to maximize profit or minimize cost, or maximize the area. What is the biggest fenced in area or box I can design while using a minimum amount of material? And let's just take a look at how we approach those kind of questions. So first of all, drawing a picture. If possible, draw a schematic picture with all the relevant information. Honestly, drawing a picture or a diagram is almost always a good idea when dealing with a math problem or a science problem. It's not necessary all the time. We just answered a number of questions without bothering to sketch the graph, and that's fine. But especially when dealing with a word problem involving some kind of shape or space, it's often very helpful. Or even just a quick sketch of our graph if we're dealing with like revenue or profit or something. So draw a picture. Determine your goal. What needs to be optimized? Are we trying to maximize profit, minimize area? What are we actually trying to do? Find constraints. What limitations are set on our optimization? So linking back to what we just talked about, we're actually identifying our endpoints here. So for example, if we're trying to find the possible areas of a shape, we know that we can't have a negative area or a zero area. Similarly, if I'm trying to find like amount of objects I can produce in my factory or whatever, I can't have a negative number. So our mathematical model might extend, you know, if we graph the whole function, but we'd know, well, I can't have a negative number of objects, or maybe if I'm finding the height of something, I know it can't go below the ground. So certain aspects of my function will be inadmissible, and so that's why we set constraints on our x value or y value. That's why we have our endpoints. We're going to solve for a single variable. Now you should have a function to optimize. So if we're talking about length and width, we can't have two different variables in our equation, so we're going to need to define everything in terms of one variable. And we've worked on problems like that before in our past lessons where we had to rewrite equations in terms of a single variable. And then use calculus to find the extreme values. Be sure to check your answer. Now we've seen these steps before. And this isn't really new. We're just putting together our pieces. We're listing, reminding ourselves of the steps to solve this kind of problem before we actually dive into it. So let's take a look at our second set of steps here, or rather we can think of these are our overall ideas to keep in mind and guide. And this is our actual algorithm. So kind of step 0, always draw a diagram if appropriate. 1, create a relevant equation, also called modeling. Modeling just means find an equation that describes your situation. What is the function? What produces a graph that describes my real life situation here? Ensure the equation is in terms of one variable only. Consider the question. You might just be able to answer it without calculus, just using the equation that you have. Or if there are telltale calculus words, then you need to take the derivative of your equation and keep going. So look for words like rate or change in. 5, if your question involves a maximum or minimum, then you'll set your derivative function equal to 0 and proceed. So it might not always require a max or min, so it's an if. Make sure, don't take the derivative if you don't need to, that's just extra work. And make sure that you answer the original question. So maybe you've done a whole bunch of work and you've solved your value for your value of x. Maybe you need to interpret that result still. So make sure you end it with a concluding statement, including units describing what you've just found. And we've seen these steps before. We've talked about telltale calculus words before. And so you're welcome to look back in your notes or previous videos. I can't remember which one exactly, but we have touched on this topic before, so this isn't new. We're just going a little deeper into optimization and working through a number of examples together. In our first example problem here for optimization, we are asked or told that of all the rectangles of area 100 centimeters squared, which has the smallest perimeter? So let's start by using our guidelines for optimization, and let's start by drawing a picture. Actually, before we even do that, let's look at the question and just think about what we're doing. We're dealing with area of a rectangle. So area is length times width for a rectangle. I know the total area is 100 centimeters squared, and it has the smallest perimeter. So we're going to be minimizing or finding our minimum value. And let's also think quickly about, what do I know about perimeter of a rectangle? Well, it's 2 times the length plus 2 times the width. So I'm just kind of quickly written out the things that I know. And let's draw a picture. I'll make it a little bit bigger. All right, so we have a rectangle. We know the area of a rectangle is 100 centimeters squared. I know that all my angles are right angles. And I'm also going to think about what my possible values are going to be here. So I want the smallest perimeter for my rectangle. Oh, that's fine. Yeah, let's keep going. So what do I know about this shape? Well, I know I'm going to want to minimize perimeter, so I'm going to want to work with my perimeter equation, but I need to define everything in terms of a single variable. So, sorry, let's go through this one piece at a time. So draw our picture, determine our goal, find constraints, solve for single variable, use calculus to solve. We've drawn our picture. Let's determine our goal. Our goal is to find our smallest perimeter. And so we're going to use our equation for perimeter of a rectangle and find our constraints. What limitations are set on our optimization? Well, I know my perimeter has to be greater than 0. Because I can't have a negative perimeter. I can't have like a negative length of fence. And solve for a single variable. So along the way, as I set up the question, I wrote out 2 equations that I know. I know that perimeter of a rectangle is 2 length plus 2 width. And I know that the area is equal to length times width. So our next step wanted us to solve for a single variable. So what I'm going to do is we're going to let x represent width. So we're going to choose to represent everything in terms of width. And so if I know area equals length times width, width equals area divided by length. And we're going to let x represent our width. So x is going to equal a over L, or L is equal to a over x. So I've defined my length in terms of area and x, and I know the area, it's going to be 100 for this question, so length is going to be 100 over x. So on my rectangle here, I have my length and my width, and let's rewrite that. So width is just going to be my x value, and length is going to be 100 over x. So I've defined each length that I'm dealing with in terms of a single variable x. And I know the formula for perimeter. Perimeter is 2 length plus 2 width. Or in other words, perimeter is 2 times 100 over x plus 2 times x. So perimeter is 200 x to the negative 1 plus 2x. So I've found my perimeter, or I found the formula that describes my perimeter of my shape. Now I need to optimize it. I need to find the minimum value. In order to do that, I'll look for that telltale calculus word, and that telltale calculus word here is minimum. And so I'm going to find the derivative of this function. So p prime, and actually I should define what this is in terms of, so I'm just going to rewrite this quickly. Perimeter as a function of x, which is the width, and then the derivative, so my changing in perimeter as my width changes is going to be equal to negative 200 x to the negative 2 plus 2, or we could rewrite it as negative 200 over x squared plus 2. And all right, I'm trying to find my minimum value now. So a minimum on my original function, my minimum on my perimeter, is going to occur when my first derivative is set equal to 0. So let's switch colors here. We're going to set our derivative equal to 0. In this case, we don't have f prime x, we have p prime x, but that's fine. So let's set our equation equal to 0. So 0 equals negative 200 over x squared plus 2. So let's rearrange. Negative 2 equals negative 200 over x squared. I'm not going to show all my steps here because we've been solving equations since grade 9. So we should have a feel for this. But x squared is going to equal 200 over 2, or x squared is going to equal 100. And we're going to take the square root of each side, and we're going to see that x is equal to plus or minus 10. Remember though, my length, my width, my perimeter, they all have to be greater than 0. I can't have a negative length. That has no meaning in this case. And so x has to be greater than 0. So the only possible x value I care about here is 10. I need to prove, though, is this a minimum? How do I know I didn't just find a maximum value? Well, that's when we're going to look at our interval, use our table and do our interval test. I'm running out of room here. I should have laid my page out a little bit better. So I'm going to pause and resize and rearrange this for a moment. All right, let's determine if this is a minimum. How do I tell if something is a minimum? Well, I could find the second derivative and check the concavity, or I can just test using a table. So let's take a look, and I'm going to work through that up here. So I'm going to have my interval, and I'm going to look at what's happening in my graph from negative infinity up to 10, what's happening at x equals 10, and what's happening after that from 10 to positive infinity. All right, I'm going to choose my test value. So remember here, I'm just choosing any value I want that fits within the interval, something nice and easy to work with. So between negative infinity and 10, I'm going to use x equals 1. At the actual point, I have x equals 10. And test value above 10, I'll use x equals 20. And it doesn't matter. I could choose 11, 12, 15, 300,000. It doesn't matter. We're just choosing some value that fits within our function there. I'm going to plug those values into my first derivative in order to figure out what is the slope at each point. And if I evaluate my function, so I'm using my derivative function here, so this one right here. So I'm plugging in my test value. So if I evaluate my first derivative at 1, then I get negative 198. I don't care about the number though, I just care about the sign. So it's negative, which means my graph is going down. If I evaluate my function at 10, that is a value of 0, which I've already proven, but still helpful to know. So I don't technically need to do this column here. We didn't do it in some of our previous examples, but I find it helpful to still include that value. And then let's evaluate our function. So our first derivative at 20, and it's a positive value, so my graph is going up. So I've confirmed that to the left of this critical point, my function is going down. To the right of this critical point, my function is going up. And that means that it's going to be a minimum. And actually, I didn't need to put this. Okay, 0 and plus. And what does that mean in terms of the shape of my original function? It means it's going down. It means it's not going up or down, and then it's going back up. So therefore, there is a minimum at x equals 10. We didn't actually answer our question yet, though. What did the question say? So it said, of all the rectangles, which has the smallest perimeter? And so I drew my picture. I determined my goal. I found my constraints. I solved for a single variable. I used calculus to find the extreme values. Now I need to actually answer the question. So the question is actually asking us, what are the dimensions of this triangle? So my x value that solves this or satisfies what the question is asking for is x equals 10. Remember, x represents my width. So we're going to have a width of x, which equals 10. And don't forget our units are in centimeters, so 10 centimeters. And my length, remember we set up here our length is 100 over x. So 100 over x, which is 100 over 10, which is 10 centimeters. So therefore, the rectangle with an area of 100 centimeters squared with the smallest perimeter is 10 centimeters by 10 centimeters, or in other words, a square. And you've probably seen before that if we have to optimize our perimeter for a rectangle, it is going to be a square. All right, there we go. So the trickiest thing is kind of getting the equations set up. What equations do I need? How do I define them in terms of a single variable? But after that, this is all stuff that we've done previously. So we're just applying things we already know how to do or have maybe seen before in a new context and using our calculus tools like first and second derivative possibly in order to confirm and test our values. All right, let's move on to an additional example. In problem 2, we are told that a piece of sheet metal, 60 centimeters by 30 centimeters, is to be used to make a rectangular box with an open top. Determine the approximate dimensions of the box that will give the box the largest volume. And so basically, we're going to think about, we're starting with a sheet of paper. How do I fold it into a box? So I could like, okay, I'm gonna fold these sides up to be the ends, and I'm gonna fold these sides up to be the sides. But I'm gonna have a problem at my corners. I can't actually like fold, like the corner's gonna get all crinkled or weird if I tried to just fold my whole sheet of paper there. And if you have a piece of paper around you on your desk, even just like a sticky note, or a post-it. Yeah, that's the word I'm trying to think of. Basically, if you have a piece of paper, go ahead and try that for a moment. Try folding it up into a little box, and you'll see that we have a problem with the corners. So what we're going to do here, and I'll draw this just a little neatlier, is we're going to actually cut the corners out of our box. I probably could have left that, but I'm not feeling satisfied with my drawing, so I would like to redo it again. And I'm going to over-exaggerate a little bit just so I have room to add my labels and everything. But basically, we're going to cut the corners out of our box in order to allow it to be able to fold, because we're starting with a single piece, and apparently we're not allowed any overlapping material, so we're going to remove these sections. And I'm going to label each piece I'm going to cut out. It's going to be a square. I'm going to label these X. So we're going to be removing 4 squares from our total area, each with an area of x squared. So we've actually already started following our guidelines. Just going to make the little check boxes here. So we started by drawing a picture. Let's define what we just described here in terms of our x. So we're going to, I think I can write it in here. Let x represent side length of our cutout squares. Second step, determine our goal. What are we asked to do here? So we're making a rectangular box with an open top. We want to determine approximate dimensions that will give you the box with the largest volume. So I want to maximize the volume. Max volume of our box. So what do we know about volume of a rectangle? Well, I know that the volume, and I'll work on the left side here so I don't run out of room this time. Volume of a rectangle is going to be length times width times height. What do I know about the length of my box in this case? Well, it's going to be this dimension right here. That's my length. And I know the length is given in the question. It's going to be 60 centimeters. Or that's like my original length. But we got to be careful. So remember, when I actually fold my box, the base of the box is going to be here. These are going to be the outside dimensions of my box. So it's not going to be 60 centimeters anymore. We're going to be subtracting 2 of our cutout squares. So my length is going to be equal to 60 minus 2x. Similarly with my width, my original width was, given in the question, 30 centimeters, but we're subtracting 2 of our cutouts, so the width of our completed box is going to be here. So our width is going to be 30 minus 2x. And what's the height of our box going to be? Well, we're going to be folding up, so this part is going to be one wall, and this part's going to be the other wall. And so our height is just going to have a value of x. So our height is equal to x. So everything's defined in terms of x. That's going to be our only variable. And we can see that here. So height is defined in terms of x. Width is defined in terms of x. Length is defined in terms of x. So we have determined our goal. We have set things up in terms of a single variable. And what are the constraints? I kind of glossed over that part, but we know that all our values have to be greater than 0. So I'll just put greater than 0. The length, the width, and the height all must be greater than 0. And then our area and our volume are greater than 0 as well. All right, we know our equation for our volume. Let's plug in our new pieces. So volume equals length, and our length is 60 minus 2x times width. My width is 30 minus 2x, and my height is just x. Let's expand and put this into polynomial form. So we're just going to multiply through everything. So we're going to do volume is 60 minus 2x, and I'm going to multiply the second and third factors together right away. So I'm going to have 30x minus 2x squared. From here, it's just double distributive property. So 60 says hello to my first term and my second term. Negative 2x says hello to my first term and my second term. And so we're going to get 1800, I should say, x minus 120x squared minus 60x squared plus 4x cubed. And we want to write this with our degree in descending order. So actually, I should write the variable as well. Oops. It's not wrong. I just want to be careful with my notation. So volume as a function of x is equal to 4x cubed minus 180x squared plus 1800x. All right, that looks pretty good to me. And do we need calculus here? Yes, because we're trying to maximize something. I want to find a maximum value. So in order to find my maximum, I'm going to set my derivative equal to 0 and work with those variables, with those values. So I think we have room to do that here. So we're going to set our function derivative equal to 0. So let's find our derivative. V prime of x is equal to 12x squared minus 360x plus 1800. And can I do any factoring? In this course, once again, we're not worried too much about like actually factoring quadratics. We're just going to worry about doing greatest common factoring. So is there a greatest common factor I can pull out of each of these terms? Yes, there is. I can pull out the 12. So we're going to factor v prime x is equal to 12, and in the brackets x squared minus 30x plus 150. And then we're going to set it equal to 0. So let's set each factor equal to 0. 12 is never going to equal 0. And when is this going to equal 0? Well, we could factor it using traditional methods, or we can just use the quadratic formula. And I don't have room to do that up here, so let's move up and do that as our next calculation step. And I'll switch colors because we're doing something new. So I have x squared minus 30x plus 150 equals 0. And we know that x equals negative b plus or minus the square root of b squared minus 4ac over 2a. And I'm not going to show all my work. We know how to do this. And to be honest, I have a program on my calculator that solves it quickly for me. So I'm going to open that program and I'm going to solve. And if we do this properly, we're going to find, once again, I'm just not showing the work, but we're using our quadratic formula, that x equals 15 plus or minus 5 root 3. And remember, we just need approximate values here for our dimensions. It says right in the question, approximate. That means I can use the decimal. I don't need the exact value. So x is going to equal either 23.7 or x is going to equal 6.3. One of these values is inadmissible. Why? I thought the only constraint we set was that our values had to be positive, and this is a positive number, so what's wrong with that? Well, let's think quickly back to our question. What do we know about the width? I know the width is equal to 30 minus 2x. And if our x value that we just found is 23.7, what's our width going to be? Well, it's going to be 30 minus 2 times 23.7. It's going to be negative 17.4. Can I have a negative width? No, I cannot. So that is why this is inadmissible. So we're only going to worry about, once again, we didn't make a calculation error. This is the limitation of our model. I'm using this function to describe the volume of this box, and it's a perfectly fine function, but it has limits. And sometimes we've gone outside our interval, we've gone outside our constraints, and so this value no longer has a physical meaning. And so we're just going to focus on this value right here. So we've solved for our single variable. We've done our optimization. What's left to do? Well, all we need to do is verify this is a max. And then answer our question. How are we going to verify? Well, we're going to use our table once again. So I'm going to have my interval and I'm going to consider the interval from negative infinity to 6.3. I'm going to look at 6.3, and I'm going to look at the interval from 6.3 to positive infinity. I'm going to choose my test values, and I'm going to use x equals 1, x equals 6.3, and x equals 10, because those are nice, easy to use points that lie within those intervals. I'm going to look at my first derivative. So remember, we've already found that over here. I'm just going to evaluate that function for my test value. So I'm going to plug x equals 1 into that function. All right, so evaluating x equals 1. And once again, I don't care about the actual number. I just care about the sign. And I find that if I evaluate at that point, the derivative, so the value of the derivative is positive 1452. All I care about is that, is that it's positive. What does that mean for the shape of my original function at that point? Well, if it has a positive value, that means the slope is positive and it's going up. So we're in an interval of increase. What happens if I evaluate my first derivative at x equals 6.3? Approximately, I should use the actual value to get the exact value, but basically, it's not going to be positive or negative. It's going to have a value of 0. And what happens when I evaluate my function for 10? I get the answer of negative 600. I don't care that it's a 600 though. All I care is that it's negative. And what does it mean when we have a negative? It means that we have a negative slope. Our graph is in an interval of decrease. So what does this mean? I have the increase-decrease pattern. That means that I have a max at x equals 6.3. And so let's actually finish answering our question. The question asks us, what are the approximate dimensions of the box? So far, all I've done is find x. I've proven that it's a maximum. I've gone through the optimization problem. Now I need to interpret my result. So I'm running out of room here. I'll kind of write it on the next page. So what do we know about our length? Well, length is equal to 60 minus 2x. What do we know about our width? It's equal to 30 minus 2x. And my height is simply equal to x. So let's plug those values in. So we said our x was 6.3, so length is 60 minus 2 times 6.3. 60 minus 2 times 6.3 is 47.4 centimeters. Our width is 30 minus 2 times 6.3, which is 17.4 centimeters, and our height is 6.3 centimeters. So let's write our concluding statement. Therefore, the largest volume occurs with approximate dimensions of 47.4 centimeters by 17.4 centimeters by 6.3 centimeters. So we've successfully interpreted our result and stated our final answer. And that is about it. And so also just as a kind of a hint or a preview that if I ask optimization questions on a test or an assignment, they will likely be very similar to this problem because we don't have time to look at a whole bunch of terribly different optimization problems. So I'm going to try to ask questions that are fair. And then our final slide here, once again, this doesn't all apply to us because this is reusing somebody else's old note, but our assignment 6, which does include questions about optimization, it has been released. Oops. So you should already be working on it. And don't worry about this stuff about release that today at 1:30. We already have it. We do have class work time tomorrow afternoon and today. It is due tomorrow by 8 p.m. So that's Thursday, April 22. In our case, the assignment is worth 60 marks because I've combined 2 assignments together. And why is single file submission so important? Please hand it in as a single PDF. I've said this before, I'm going to say it again. If you hand your assignment in as 5 different pictures, I need to download the pictures. They all download in a zip folder. I need to extract the zip folder. I need to select all the pictures. I need to export them as a single PDF, and then I can start working. Even if that takes 2 minutes, there are about 30 of you in this class. 30 times 2 is an hour of work just to prepare your files before I even start marking. So, especially with the quadmester system, I really have to maximize my time. So please, I need to optimize my time. So please help me optimize my time and my workflow by submitting your work as a single file, submitted to the appropriate place on Brightspace as much as possible. And if you do have issues, then you can just email me and I can assist you from there. But single file submissions directly to Brightspace are the easiest and best way to get your work handed in.